Super Smash Bros. Ultimate, or really the whole Smash series, has some ridiculous moves and abilities in it. Back during my first year of YouTube, I calculated how strong a Falcon Punch would actually have to be, based on the fact that his fist catches fire. Then, much more recently, we calculated how fast Link would actually have to spin to achieve lift. It's crazy. And maybe this will actually become a series of videos where we calculate such smashy things. Just need one of them to do well. So share this video around. But those things are cool. What are we figuring out today? Well, the power of Villager's tree, obviously. And I don't just mean a tree falling on you or anything. No, that'd be lame. And we're not lame. No, rather we're asking the question, what does it take for a tree to grow that big, that fast? How much energy would it need? And what would theoretically happen if it did go as fast as Villager's tree does? I mean, that's ridiculous. Can we even calculate something like that? Well, I'm Lockstin, and this is Smash Science, a series on Gnoggin, and I say, well, we can give it a shot. How does a tree even grow, should be the first question. I mean, have you ever watched a tree grow? It's incredibly slow. I mean, some trees are even able to grow taller than the Statue of Liberty. It takes them a long time to get there. And yeah, that's a true fun fact. Some redwood trees have been measured up to 397 feet tall. It's incredible. As a kid, I always wanted to know, how do they even get that big? Even just an oak or a pine. As a kid, I thought they just used the dirt or soil around them, sucked it all up through their roots. And man, was I a dumb child? You can obviously see that the dirt around the trees does not disappear, yet they still grow large. This is all due to the fact that they intake carbon, specifically CO2, during photosynthesis. That's right, the way they even live at all is also how they grow. Shocking. Really, it's just like humans, like myself. We eat more, the more you grow. Kids need nutrients to get big. Trees then just eat carbon, mainly. In fact, they don't even use the soil itself. Sure, they may use some of the nutrients in the soil, but the soil itself is just used as an anchor. It's never actually absorbed into the plant. But notably, their growth is over many years. Trees are simple creatures. Are they creatures? Well, regardless of what they are simple. They are actually made up of about 6 elements, or at least 98% of them is made of those 6. Those 6 being carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Being simple life forms, it should be pretty easy to figure out how much energy they need to grow. Unfortunately though, it's not. Even the most simple forms of life all have variants and variables that change everything about them. But hey, this is a video game theory. And those last 2 words next to each other basically means we can make all of the wild assumptions we want. As long as we're entertaining. Unfortunately though, there isn't much data about this topic actually, and I don't have the time to watch a tree grow to maturity and then make this video. So this means that we're calculating in rough estimates. This may not be exactly the same as Villager's tree, but rather just trees in general. Roughly the right size, so lots of rough estimates. And the reason it's so complicated is because trees produce their own food from the sun and nutrients found around them. So it's rather hard to calculate how much energy they actually take in daily, along with the fact that trees need more energy the larger they grow. But thankfully, the nice people of North Carolina University figured out that the average tree takes in about 45 pounds of carbon dioxide a year. Then it uses said CO2 in photosynthesis. This can be quickly summed up in the equation I'm putting on screen, because I don't want to say it. Look at all that. That's how you know this video is going to be complicated. Basically, what all this means is that it's taking carbon dioxide and water to make glucose, or food, with the byproduct of oxygen. And this is all powered by the sun. Now you're thinking, well, energy is just from the glucose, not the sun. Where does the sun come into play, scientifically speaking? Well, remember when I said powered by the sun? Well, the energy in glucose was put there by the sun. Anytime you are breaking or making bonds with chemicals, you need to put energy into it. And that's the energy from the sun. The energy that's actually making the stuff. Conversion of energy, yo! Though it should be mentioned that that's in a really, really efficient system. In real life, the plant may be better or worse, usually worse, thanks to life being so darn unpredictable and all. Here's a fun fact about trees' solar absorption. Only 0.1% of the sun's energy is trapped by organisms at all. And of that 0.1%, trees account for half of it. So trees are better at absorbing sun energy than most animals, for sure. Or at least there are a ton of trees. Probably the latter. Now, glucose does a number of things. I mean, it's the leading cause of the obesity and diabetes epidemic, so there's that. Thanks. But in trees specifically, it can be used for fruit or seeds of the tree, obviously. It could also be turned into starch for the roots or cell walls, which helps growth. More biomass means bigger tree, but its main function is to be used as a starting chemical to create ATP, or adenosine triphosphate, which is pretty much one of the main forms of energy for most cells. Basically, it's what the mitochondria makes, and we all know what that is, the powerhouse of our cells. But in plants, it's produced by the chloroplast during photosynthesis. Unfortunately, it's pretty hard to figure out exactly what a plant does with its glucose, but this is a video game, so let's assume it's using all of it to grow. And I'm saying all of it. I mean, the tree grows in a second. Compare that to normal trees. Even the really fast-growing trees take up to 10 to 15 years to reach maturity. I mean, let's quickly look at the frame data. This tree's growth actually starts only after a few frames of water hitting the sapling. It then starts to rapidly grow in size, and upon frame 10, after it has started, its hitbox becomes a hurt box. But we see that only happens about halfway into its growth. In fact, it isn't fully grown until about frame 20 or 30. Also, for you nerds out there, it does about 14% damage, if you wanted to know. Also, just a note, this is data from Smash 4. Hopefully it's not too off from the new Smash Bros. Game. This was all made before Ultimate's release. So the next calculations are gonna get a little bit weird because of, well, one, that's really fast for a tree to reach maturity! Half a second? And two, there just isn't all that much information. But I'll try my best for you, because you deserve the best. Now I'm gonna take a step back and state that trees are not that efficient. Did you know that most of the energy they make is lost as latent heat? Yeah, they just get warmer. That's all they do. I mean, them getting warmer moves the water around inside of them via something similar to evaporation. This in turn takes all the nutrients and sap up from the roots and trunk into the leaves. But I mean, they also just get warm, and generating warmth uses a ton of energy. Fun fact, a large tree is actually able to transport up to 100 gallons of water and disperse it in the air as oxygen per day. That's crazy. Water is heavy. Remember when I said that some trees grow almost 400 feet? Imagine carrying 100 gallons of water up 40 flights of stairs a day. I'm tired just thinking about putting a few gallons of water in my fish tank. Other major complications that affect all of this math is that trees don't grow constantly. You all know that time of year called winter. Most trees just kind of exist, living off of stores of sap they created during the other seasons. At this time, their growth slows greatly, even stopping. So instead of the energy going to growth, they use it just to survive. And other times, they use the energy for other things, like repairing branches or replacing leaves and twigs and other tree things that they do. Thankfully, people scientists have done papers on this stuff because trees are cool. They found that on average, and we're talking rough average, depending on the season, trees can use up to 80% of their glucose on either growth or storage for use in winter. I'm gonna use this percent as almost a blanket number, just to cover how much of their glucose they use for just growing, as I'm assuming Villager's tree is growing in the magically induced super spring. No matter what you do or what you say, magic is going on. But even magic sometimes can be explained with a bit of science, and that's awesome. That's what we're here doing today. So now, it's time to begin the calculations. So we know that trees take in, on average, 48 pounds of CO2 a year. It takes trees about 10 to 15 years to grow, just to maturity, so let's just go with 10. It's a fast-growing tree, because it's a super fast-growing tree. So that's a total of 480 pounds of CO2 for its growth. Only problem is, that the 48-pound number comes from a full-grown tree, but we can ignore that, I guess? Let's just ignore that. Let's keep things simple. Unfortunately, it's not just a linear equation for CO2 intake, but that's all complicated. We're dealing with magic. Let's assume magic's going on. We know that trees make glucose with this equation. 6 molecules of carbon dioxide plus 6 molecules of water powered by the sun's energy to make 1 molecule of glucose, plus 6 molecules of oxygen. And because we know the formula for glucose, we can now say that the glucose mass is about 40% carbon. With carbon's weight of 12 and oxygen 16, carbon makes up about 37% of CO2 because remember, there's 2 oxygen molecules. So all in all, that gives us about 177.6 pounds of carbon from the CO2 the tree has absorbed over its lifetime to maturity. We then can basically convert that into glucose. Also remember, glucose is made of more than just carbon, so it should be more than our 177.6 pounds. Quick math magic, and we end up with about 444 pounds of glucose. Wow. That's a lot of sugar. Pretty sure that'd kill me. Or anyone for that matter. This is roughly 976.8 kilos for you across the pond, or the border, or anywhere else. And remember, the tree only uses about 80% of its glucose for growth, during grow times at that, so we have to do a little more math. We end up with 781.4 kilograms, or 781,444 grams of glucose. I converted to grams because there are about 4 calories in each gram of glucose, and those are technically kilocalories, basically the ones we talk about when we talk about food. So, that means this tree basically uses 3,125,760 calories instantly, or near instantly, which tends to be more than the recommended daily intake of calories, that being 2,000. In fact, that's approximately 1,562 days worth of food. That's more than 4 years. Wait, we can go deeper. There's about 4,184 joules in every calorie. And to keep it simple, a joule is basically a tiny measurement of energy. Just energy. Just leave it at that. It's complicated. So that means we're talking 13,78,179,840 joules. That's a lot of power, right? Well, I mean, let's talk in terms of TNT, because why not explosions? This tree is using the same amount of energy that 3.12 tons of TNT give off in an explosion. That's 3.12 metric tons, so 3,120 kilos of TNT. Just used up by a tree in like half of a second! I mean, imagine the friction! It probably would explode like a bomb. The thing takes in about the same amount of energy as the GBU-57 American bomb, nicknamed the Bunker Buster, a bomb dropped on bunkers. And this tree uses up all of that energy in half of a second. Just imagine for a moment the amount of air the tree is pulling into itself magically in this moment. I'm pretty sure it would have a suction force of something insane. I mean, it's pulling in 177.6 pounds of CO2 out of the air. CO2 concentration is about 0.0383 by volume in our atmosphere, and a pound of air is 0.35 meters cubed. That means it would take about 5,920 pounds of air to get 177.6 pounds of CO2, meaning that the total volume of air sucked into that tree was 2,072 meters, or about 2 kilometers cubed. Yeah, that's crazy. I'm sure that would cause some sort of implosion, or at least be a little destructive. The entire stage and everything around it gets rapidly sucked into the tree and then blasted upwards as it basically explodes. That's what would happen if Smash were realistic. Thanks, Sakurai, it's not. I hope that helps you understand how much of a crazy move Villager's tree is. I mean, what's even in that water? So the next time you see those soulless, unflinching eyes filled with murder, just remember, 3 tons of TNT. That's the energy of a tree. It rhymes. So you know it's true. Now then, outro stuff. Let me know down below, should I do more Smash science? If there's enough interest in this series, then we'll keep it up. Just keep figuring out weirdo science fun fact stuff, and keep it up alongside the usual Pokemon content. So, until next time, you never stop using that noggin.